So in part 3, what we're going to do now is turn to Python. Okay, ODE, what is it? It's ODE solve. I think that's the name of it. Let me just double check. Oh, so we'll just do this, ODE solver. It's actually called solve IVP. That's what it's called. Okay, and what we're going to learn to solve in the Python solver is we're going to learn to solve equations, ODE IVPs, of the form d dt of d, let's see, I've been rewriting it slightly different. Let me just do this. dy dt is equal to some function of t comma y, and I don't remember, sometimes I write yt, sometimes ty, it doesn't matter how you write them, okay, where y at 0 is equal to some constant vector y0. All right, and where this one, remember, y goes from y0, y1, all the way to yn minus 1. And this guy here, f, is this vector of functions, f0, f1, fn minus 1. Okay? All right, so let's turn our attention to Python now and have a look at that and see what's going on. Okay, so here we are. Let me actually fix something real quick so I can make sure I don't cover something up. Sometimes I do that. All right, let me just look at that. All right, so we're looking here at the Python example, and in Python, we're going to go back to the Scipy.Integrate module. So you remember the Scipy.Integrate module from earlier, and the Scipy.Integrate module has, we did things like quadrature and simps, and now we're going to use the solve IVP function. And the solve IVP function assumes that our system is in the form that I've just described. dy dt is equal to f t comma y. All right, and so to solve it, we're going to do these 5 steps. So you need to import solve IVP. We've imported lots of things. Hopefully that's easy by now. We need to define a function for the right-hand side. So you're not going to have to write out this derivative. You just need to define a function that is what that piece is on the right-hand side. All right, and then and you need to make sure that this is in that standard form. All right, and so that standard form is going to actually have t comma y, where y is a vector, and we'll see that in the vectors. We're going to do it with just a simple single equation first, and then we'll do it for vectors. Okay, then you're going to create an array of times over which you want to solve this ODE. All right, and then you need to define an array with an initial condition, so you need to define what the initial conditions are, and then you call the function solve IVP. Right? It returns a dictionary object, okay, that has the time as one of the things in the solution, and then the y values at the times that it's solved for. All right, and so I'm going to show an example down here of how to do that. But for more information, don't forget to check out the documentation online. The Python documentation, I think, is really well done, really readable. All right, so I'm going to solve a system which is dc dt is equal to minus c over tau. Okay, and notice that this is just like really simple. This is linear. You can integrate this. I think we solved this one last time. This is just exponential decay is what it's going to give us out, and you can see here I've solved for what it is. It's just exponential function. All right, and we're going to solve this assuming that we know tau is equal to 1. That the initial concentration C here is equal to 1, and we're going to solve it out to the time point 5. Okay, so what do? We do these 5 steps. We import it. So from Scipy.Integrate, we import solve IVP. And then we define our function, which is just the right-hand side. Notice that this has to be in the standard form, t comma whatever the y value is. All right, in this case, I called it c instead of y. but that's the same thing. So the t needs to come first in Python solve IVP. Then I need to define the range of time points I want to do. And it turns out that solve IVP in this range here, it doesn't ask for all the intermediate points. It just wants the beginning and the end. So you don't need to give it all the intermediate points. It actually is going to determine those for itself. All right, it's using some kind of adaptive time stepping scheme in its general case, and so it doesn't necessarily have the same width delta t, but we'll show in a minute how you can do that. And then you need to set the initial condition. Importantly, even for the case of just a single ODE, you need to make your initial condition an array. For whatever reason, that's what the function needs. So you need to define it as an array with just one value in it. Okay, and then you solve the problem. So you can do this. You say solution is equal to solve IVP. You give it the name of the function that you defined. You give it the time range that you care about, and you give it the initial condition, and it solves it. So let's run it and see what happens. So I run that guy, okay, and then I plot it, and you can see, I'm going to pull my keyboard over here, and you can see that I indeed do get this answer out, and you can see that the solution returns this dictionary, so I need to give it solution.t, and then the solution.y, and y also will return an array in general, because as we're going to see, we're going to solve these array problems, and so we kind of have to deal with the arrays even when we don't care, which is one reason we learned about arrays and the solutions for that before doing this in Python. All right, and then here's our exact solution, and you can see that our orange solve IVP dots overlap very well with the exact solution. Okay, so now suppose you want to do time points that you know about. Suppose you don't want to have these way spaced out. Maybe you have some exact time that you want to do, or maybe you're going to do some interpolation later for this function and you'd like to have evenly spaced points. You can do that. It turns out you do the same thing that you did before, all the same steps, except you have to define a brand new array in addition to this time span. So the time span, which has the beginning and the end array, that's one thing, but you need to define a new array, which is the times, that are all the times that you want. And you give it an extra argument when you call solve IVP right here on line 107, where you say t_eval, which is the time it's going to evaluate at, and you make that equal to the times that you put up here. And when I run this one now, you can see it's evaluated at all of these 50 time points that I put in between. All right, and so you can see that the time that it's returned for this concentration are now, all at those 50 points. Whereas previously up here, when I run this one, the concentration it returns is only at a few points. All right, so this takes a little bit extra work to do that, but it turns out that the solve IVP function is still pretty good at doing that. Okay, that's still pretty easy. All right, so what I want you to do is to pause the video and take a look at this practice. So here is a first order initial value problem that's nonlinear. It has cosines and squares and stuff in it. And I want you to practice on your own. Try and type it on your own. Don't just copy and paste from above. Look above and then maybe cover it up and then try and type it so you can try and remember. It turns out that the remembering is an important part of learning as you're trying to struggle to do that. Okay, the key is down below. I'm not going to scroll down there and show you the key, but it's down there and you can see what the answer is on how to do it. All right, so take a minute, pause the video, try and do this practice to practice getting used to the syntax yourself. If you do that practice, I promise you that you're going to have an easier time getting the next little bit here where I'm going to go into the examples of doing the systems of ODEs. All right. So hopefully you did that practice. Hopefully you got the answer right, and now you understand what's going on. Let's turn and do an example now of systems of ODEs. So systems of ODEs, I've typed all this stuff up, but it's a lot the same. Okay, so it's still the same function, solve IVP, and it's still the same format, dy dt is equal to f t comma y, with an initial condition, but now these things are arrays, just like we saw before. So now if you have a system of equations or you have higher order ODEs, all you have to do is convert it to that standard form, Once you're in the standard form, then you put it into the system just like we did with single ODEs. Okay, so the same 5 steps that we did before. Import it, define the right-hand side function, choose a span of time that you care about. Okay, define an array of initial conditions. Now we definitely see why we need an array. Okay, and then find the solution using IVP. That's the same 5 steps. So let's look at our example that we did earlier in the lecture, where I have dAdt is minus KAB, where dBdt is minus KAB, and dCdt is plus KAB. And I've got this 2, 1, 0 initial condition. All right, and I'm going to solve this for k is equal to 0.1, and I'm going to put the time from 0 to 50. So the first thing I do, right, is I convert that to standard form. And when I go to define the function, notice that I have to give it t comma y. All right, and when I do function t comma y is now assumed to be a vector. And to make my life a little easier to remember this a and b, I actually just make a and b variables here to hold y0, y1, and y2, so I can rewrite this exactly how I did above. Okay, now I make k here. This is giving me this little warning because it says I'm defining a variable c because it's never used, and it's true. It is never used on the right-hand side, but I'm showing it here for completeness so that you can see what I would do if there was a c used over here. All right. Now what I do, is I define the functions for the right-hand side, and I return them as an array. So hopefully this is tickling your memory and reminding you of when we solved systems of nonlinear equations using arrays. Do you remember doing that? And we had to define the function up at the top as an array input with the different variables. And then at the bottom I had to return the function, and I had f0, f1, f2. I could have just as easily called this, f0, f1, f2. All right, in this particular example, I called it dAdt, dBdt, dCdt, and then, but they're just the same as those right-hand side functions that I had. All right, so the hardest part I think about this is setting up the function. Make sure that you set up the function similar to how we did nonlinear equations in the past. All right, so then now you set the times. The time you set the exact same way. So here I set up a span of times from 0 to 50. And I decided to evaluate them at 101 points internally, so I'm going to specify that array for myself. I set the initial conditions. Note that the initial conditions have to correspond with the right position. So the initial condition for y0 needs to come in the first spot, the initial condition for y1 in the second spot, for y2 in the third spot. So that's the same up here. So I called A was 2, that became y0, and so that one needs to be 2. So if you mess that order up, you're effectively setting initial conditions for the wrong variables. Then I call solve IVP. Solve IVP looks exactly the same as I did before. I call it my function, the span of times, the initial condition array, and then here I give it t-eval to give it what times I want to evaluate at in the middle. Okay, then I get my dictionary back, which I call solution, and I'm assigned t, a, b, c to be the values of that solution, and we can look and see what the concentration is. And that's a little small, so I'm going to make it bigger while we're doing this. Let's do plot.figure. Let's make it, 12 by 8. And let's make that size 24 so we can really see that puppy. I need to put fig size there. It did not like that. Equals. Man, it sure made my thing bigger, but it didn't like my figure size being bigger, huh? Maybe I need to make it a little bigger. Let me just try one more thing. Well, for some reason, it does not like doing that. Well, that's kind of a bummer. All right, we'll just make it go back down. All right, so hopefully you can see that there. It's a little bit small. You can zoom in. But what you can see is that A goes down, B goes down, and C goes up over time. All right, in the sort of simple way we'd expect. Okay, so last thing is to show how do we do higher order ODEs. So if I have something here, kind of like the example I gave you to work through where I have a second order derivative and a first order derivative all together, you can put these all together and convert them into standard form. And again, that's the hardest part is in doing this, is converting that to standard form. So I define G, the gravitational constant. This C value is 0.01 inverse meters. The endpoint I want to solve out to is 10 seconds. and I know the initial velocity is 0, and I'm going to say my initial position is 250 meters. So this is like dropping an object from a height, and now it's 250 meters up, but there's actually a little bit of drag sort of blowing back on that object. Okay, so I can rewrite that by defining a velocity as dx dt, and I end up getting dv dt, which comes from this guy, is minus g, moving it over here, plus c over m v squared. And that comes because I have a dx dt squared here. That v squared is my drag term that moves over to the right-hand side, and I get a plus. Okay, so the v squared comes because I have dx dt squared, and I called v dx dt, so that's a squared right there. And then dx dt is equal to v. So now I can write that in standard form, and I probably should switch that around because t comes first in Python in standard form. So don't let me screw that up. Okay, so I have t y0 y1, and make sure I've got my f0 and my f1 straightened out. Right, f1 is just right there. It's v, which is that guy. It looks like I'm calling y0 equal to v and y1 equal to x. Okay, so as long as that's all worked out, oh, this should be 250 right there. I said 250 up there in my answer. Okay, and I said that. So now I need to go through and call this guy, right? So I have this in standard form. So what do? I import solve IVP from the Scipy.Integrate module. I define my function. The hardest part of the Python problem is defining the function. So ft comma y. Notice that I said y0 was v right there. Okay, and x was y1 right there. And g and c were just constants that I defined up here. And so I say dv dt is equal to minus g plus c v squared. And it looks like I set m. Did I not set an m anywhere? I don't know where this m came from in this particular problem. I didn't have an m up here. So sorry about that. You can just imagine there is a mass there, but m equals 1. So that's what's going on with that. So I just set m equal to 1. That guy goes away, and I have cv squared, just like that. And dx dt is equal to v. All right, so that's the same as this guy up here. Right, so now I'm going to solve this using going from 0 to 10 seconds. I'm going to set my time, so I have 101 points, so I get some nice intermediate values to look at. And I'm going to set my initial condition. Note that the initial velocity is 0, and the initial position is 250. All right, so what are we going to see out of this? Let's think about that for a second. Well, let's actually finish this, and then we'll talk about what we're going to see. So I call my solution, right? I say solution is equal to solve IVP, function, the span of times, the initial conditions, and then t-eval at all the times I want it to evaluate at. I'm going to get out a solution there of t, v is my y0, and x is my y1. Okay, so now I'm going to make two plots here. I'm going to get a plot which is the plot of v versus time, and also a plot of x versus time. And I just put them on two separate axes. This is kind of a fun thing to do. So I use what's called the subplots feature of Python Matplotlib to do that. All right, so what do I expect to see? I start out at 0, so I expect to see my position fall, right? So I'd expect to see my position go down. I'd expect the velocity to go up, right? I'd expect the velocity to start out at 0 and to go up, but I would think that the velocity is going to level off at some point. Okay, so let's look at what happens here. And notice that the velocity, the magnitude of the velocity goes up. It's actually a negative velocity, right? So that makes sense. I'm going down, so the velocity is in the down direction. And the velocity goes up, but then the velocity levels off. And you've probably heard of this before. This is the terminal velocity, right? So the velocity goes up and up and up, and then drag opposes it, and you can find the terminal velocity there. And it turns out you can solve for that terminal velocity by setting this guy equal to 0, right? And you can find what the terminal velocity is. And the terminal velocity should be g divided by c, which is 9.8 divided by 0.01 to the square root. So we could check that, and hopefully that should come out to be the point where that's leveling off at. Maybe we'll check that in just a second and see. Okay, and then the position, what's happening with the position? So the position's falling, and it starts falling faster and faster and faster until the velocity becomes about constant, and then it starts to fall at a constant rate, right? So it starts out kind of looking like a parabola, but then it starts to look linear as this becomes a constant, and then it falls and falls and falls, and then splat, okay, hits the ground. So let's just check and see real quick. So I said that our terminal velocity should equal, I should set that equal to 0. So it should be g divided by c, take the square root. So let's make a plot of that. So I can take the 0, 1, and make a plot, I said, of t, and then I said that it should be, well, that should be parentheses, t comma, and then I said it should be g divided by c, lumpy to square root of that. And I'm going to multiply it, so that's just going to be a single value. I'm going to multiply it by 1s, which is the length of t, so that I get something out. As that, I'm going to make it, let's make it be a black dashed line there as well. And let's run that and see what happens. Name G is not defined. How is G not defined? Did I not define G in here anywhere? That is a bummer. Let's define G. Define G up here. It's equal to 9.8 meters per second squared. So apparently G worked because I had run it in this one before, and I had a G lying around. So let's try that now. Let's see what happens. C is not defined. Oh my goodness. Where did that go? Did I delete something? C should be 0.01, and that should be inverse meters. Let's run that one. And did I forget a numpy on my ones? I totally forgot a numpy on my ones. np.ones. And I need to make it negative, right? Make it negative, and voila, there we go. Okay, I'm reaching my terminal velocity. Whew, I was getting nervous for a second. Okay, so that's my examples I have for you. That's how to solve for differential equations using NumPy's, using Scipy's integrate module, the solve IVP function. And I think that's all I have for you for example 2. Or for lecture 22 for both examples. So remember, the idea here is that we can solve for a single first order differential equation initial value problem, or a system, or we can turn a higher order set of equation or set of equations into a system, and then we can solve that using solve IVP. It's very powerful. We can solve lots of kind of problems with this, and you'll encounter it all the time in the chemical engineering curriculum. With that, thank you for attention, and hope you have a great day.